Hello friends, my name is Chinmay Deshpande. In this video lecture, we are going to discuss about a topic from energy control. The name of a topic is economy interchange between interconnected utility. We will discuss here one numerical also. Now the electric power system is interconnected with each other and it gains some important advantage of being reliable and better operating of the system. Already in a previous video session, we discussed in detail about what are the advantages of interconnection or interchange of the power. Now what happens because of this interconnection? The operating cost would be the same as that of operating cost of the single unit. A load change in the overall interconnected system is taken care by all other remaining units which are there in an interconnection system. So due to this, there should not be any burden on the other unit or other system. The other unit in the interconnected system may act as a spinning reserve throughout the interconnection. The isolated system may have some disadvantages, and what are the disadvantages? That also we have gone through in the previous video lecture. Those who want, they can check that video session. But the main disadvantage of isolated system is that if the generator fails to operate, then there is no any other power source which will serve the load demand. So therefore, it affects the reliability of the system. Under such situation, some extra spinning reserve generators have to be run, which would lead to less economic operation. Now these are the advantages which are listed here also in a short. What happens because of interconnected of a system? We will get some more reliability, then less energy generation cost, spinning reserve capacity can be shared, and better utilization of the generators. I am not going to go into detail about these topics because we have seen this already. The better economics of the operation can be attained when the utilities are interconnected. Yes, definitely the opportunities may arise whenever two power systems are operating with different incremental cost. Incremental cost means what? It is a cost of a generation, and already we have seen this. Whenever we talked about a cost of a generation, then the major part it includes is nothing but a fuel cost. If a sufficient difference in the cost exists, then it pays to have both systems exchange power at an equitable price. So for that case, let's have a look for one example. Let us consider that this is your utility A and this will be utility B. As in the diagram, it is shown that there are three generators 1, 2 and 3 in the utility A. And there are again three generators 4, 5 and 6 in utility B. Consider that the utility A is generating at a lower incremental cost than utility B. Now if a utility B buys the next megawatt for its load from utility A, instead of generating itself, it will save the money in supplying the incremental load. Utility A will gain some benefit only when power required to utility B is produced and when utility A is going to sell that power to utility B, but with a higher cost. That is, cost which is greater than that of a cost of their production. So in this situation, utility B has to ready to pay this higher cost to utility A. I will give you a very simple example. Suppose the cost of a generation to the utility A is, I'll write it here, suppose 100 rupees per hour, let's say. Now utility B has demanded some kind of a power. Some surplus amount of the energy is there. So I will write it here, surplus amount of the power is there with utility A. Now utility A will think that this is the chance to get some kind of benefit. So therefore, as the 100 rupees per hour is the cost of generation for all the generators in utility A, the utility A will think that why not to sell this power to utility B with a cost of 105 rupees per hour. So there will be a benefit of rupees 5. But on the other hand, this utility B should also be ready to pay this higher cost to utility A. Then only this interchange will take place. This is the data which is given to us. In a utility A, we have three generators. So, or unit, that is 1, 2 and 3 with its unit cost function which is given. The generator limits are also given. For the generator 1, it is minimum it produces 150 megawatt, maximum it produces 600 megawatt. For generator G2, minimum it produces 100 megawatt, maximum it produces 400 megawatt. And for the generator 3, minimum it produces 50 megawatt and maximum it produces 200 megawatt. So if you see here the total demand, if you see what is the total demand? Total demand is nothing but this will be a 300 minimum. If I add this, maximum it will be 1200. So what is the load demand which is to be imposed on the generator 1 to the generator, we can say to the area A1, suppose one bus is there and to which load is connected and the demand is suppose 700 megawatt. Similarly for utility B also the data has been given, generating units and the cost function. So for generator G4, minimum generation is 140 megawatt, maximum is 590. Then for generator G5, minimum is 110, maximum is 440. And for generator we can say 6, minimum generation is 110, maximum generation is 440. So if you see here, the total generation will be what? 360 or a minimum. Yeah, we have added this 140 plus 110 plus 110. And here maximum generation for area B is 1470. Now the load demand which is to be there for load B or which is to be there for utility B is 1100. Now what we will do, we will first solve this numerical for area A, that is utility A. We will find it out what is the generation PG1, PG2, PG3 for satisfying this demand of 700. Then we will recalculate it again for area B. Again we will see what will be the generation PG4, PG5 and PG6 in order to fulfill this 1100. And after that we will think about this. A and B are interconnected with each other, so it forms a total system. So the total load demand on the system will be 700 plus 1100, which will be 1800. And instead of having 3 generators, now as it is interconnected, there will be 6 generators. So what will be the cost of a generation and how much power will be generated from generator G1 to generator G6. So first we will assume that each area operates independently, that is each will supply its load from own generators. So we will go for first utility A. Now as we know there are 3 generators, so we have to find it out PG1, PG2 and PG3, and for that case we have to find it out value of a lambda, that is Lagrange's multiplier, and its corresponding cost of a function. So for utility A, now we know that the coordination equation for the lossless line is dCi upon dPgi equal to lambda. We have gone through this equation in unit number 5, that is economic load dispatch. Consider this as a equation number 1. Now I will take this cost equation is nothing but Ci will be equal to half into Ai Pgi square plus Bi into Pgi plus Di. Now what I will do, I will differentiate this equation number 2 with respect to Pgi. So what I will get, this half Ai Pgi, so 2 will get cancelled and we will get Ai Pgi only, and plus with respect to Pgi we are taking, so therefore derivative with respect to this will be 1, so we will get Bi only. Di is the constant term, so it will not be there. So what we will get, dCi upon dPgi equal to Ai Pgi plus Bi. Now this is your equation number 1. This is your equation. If I have not given number, it's okay, or we will equate these. Let's say this is 2a. I will say this is 2a. So we will equate these. Left hand side is same. So we will equate. What we will get, Ai Pgi plus Bi will be equal to lambda. This is your lambda. So from this case we will derive a formula for a Pgi. Mark this as a important. This is very important. Pgi will be equal to what? Lambda minus Bi upon Ai, where I equal to 1, 2, 3. When we put 1, then we will get Pg1. When we put 2, we will get Pg2. When we put 3, we will get Pg3. This is your equation number 3. Now we know for a lossless line, What is your equality constraint? Whatever will be demand, that much amount of generation should be there. So instead of writing only PG, here I have written PGI, I equal to 1 to n. Here n is nothing but how many generators are there. Here we have 3 generators. So PGI equal to PD. So how I can write? We know already in the previous slide we discussed the formula of PGI. What was that? It was lambda minus BI upon AI. So I have substituted here PGI equal to what? Lambda minus BI upon AI equal to PD. So from this equation number 4, now I will try to write a formula for lambda. For that case, what I will do, I will separate these. So I will get, I write it here, this step, summation I equal to 1 to n, 1 upon AI, lambda is a constant, so lambda will be outside, minus summation I equal to 1 to n, BI upon AI, which will be equal to PD. So if I move this particular term to right hand side, we will get this PD plus summation I equal to 1 to n BI upon AI, and then I have to write a formula for lambda. So after shifting this term towards right hand side, after shifting this term, okay, let me take a pointer. After shifting this term towards right hand side, then I will shift this term towards right hand side also, which will get at a divided term. So summation I equal to 1 to n 1 upon AI. So this is the formula of lambda which we are going to use here for further calculation. What we will do now? We will equate the given cost equation from area A to equation number 2 in order to find it out value AI, BI and DI. So we know what is the equation of CI, half AI PGI square plus BI PGI plus DI. So I equal to 1 means we will get a cost equation for first generator, which is A1 PG1 square plus B1 PG1 plus D1. Now what was the first equation? Here I will write it here. Okay, let me write it here. 0.003124 into PG1 square plus 15.84 into PG1. This was the equation earlier which is given to us. This is 1122. So let me compare this. What I will do, I will compare this and this term. So I have written like this. So PG1 square will get cancelled. So how we can find it out? A1 0.003124. If I shift this 2 towards this side, it will be multiplied. So I will get A1 equal to 0.006248. Similarly, let me compare these two values. This is your 15.84 PG1. I will compare it with this B1 into PG1. So I will get directly answer for this, which is equal to 15.84. And but obvious D1 will be equal to 1122, which is not required for us in a calculator or calculation. Similarly, we can do it for I equal to 2 and I equal to 3. Likewise, you can write the steps. Directly, I have made a one table. Let's see that. So these are the values for cost equation. We can say for a generator unit 1 equation, we got these values of AI, BI and DI. Similarly, if you compare whatever this equation we have with our equation half into AI PGI square plus BI into PGI plus DI. So if you compare this half A2 PG2 square, compare it with 0.003880 PG2 square. So we will get these values. A2 will be equal to what? 0.00776. B2 is 15.70 and D2 will be equal to 620. Similarly, for unit 3 equation, we will get the value of A3, then B3 and D3. Now, how we can write? So from the equation number 5, this was the equation for finding out a value of a lambda. So summation I equal to 1 to n, as I already discussed, there are 3 generators. So it will be what? B1 upon A1 plus B2 upon A2 plus B3 upon A3 whole divided by 1 upon A1 plus 1 upon A2 plus 1 upon A3. Now we know all the values. Already in the previous slide we have gone through what is B1, B2, B3, what is A1, A2, A3. Here PD is nothing but a load demand, and this load demand in a area A, it is 700. So we have to put it here 700. So let us put all the values, and after putting we will get these answers. PD is 700. If you solve this term, which is B1 upon A1 plus B2 upon A2 plus B3 upon A3, we will get this answer. If you solve this term 1 upon A1 plus 1 upon A2 plus 1 upon A3, we will get answer as 340.7844. So after substituting, we will get answer of a lambda, which is 17.8564. Now let us put this value of lambda in the formula. We have gone through this formula. PGI equal to lambda minus BI upon AI. So what we have to do? Put this lambda, okay, let me write this first step here. PG1 will be equal to, what is lambda? It is 17.8564 minus, now here I equal to 1 I am going to substitute. So what we have to write here? B1 upon A1. So what is a B1 in case of generator 1? It will be 15.84 divided by, what is A1? This is 0.006248. So if we solve these, then we will get answer for PG1, that is 322.7215. Now let us check whether that particular value lie within a generator limit or not. Because we have this generator limit, inequality limit PG1, it was minimum it should produce 150, maximum it produced 600. This was given in the table in a given data. So as our answer lies in between these two, so it's okay. But if we got the answer which is less than 150, then we have to consider answer as a 150. If we got here answer which is more than 600, which is upper limit of a generator, then we need to consider there a maximum generation will be 600 megawatt. Similarly, you just vary here I equal to 2, B2, A2, you will get PG2 which is 277.8820, again which will lie within the limit inequality constant which is given in the numerical. Then PG3 will be equal to 99.3965. So this is the generation by that particular generator. If you add these, then you will get a total generation will be equal to 700 megawatt, which was our demand earlier, which was given in the numerical as a given. Now by putting this equation in the cost equation, now what was the cost equation? We know that if F1 or C1, it was given as 0.003124 into PG1 square plus 15.84 into PG1 plus 1122. Now what you have to do, just substitute answer of PG1 what you got earlier in this, you will get a cost of a generation. So what was the PG1? PG1 was 322.7215. So if you substitute here, you will get a cost of a generation by generator 1. So you can write it as FG1 also or CG1 also. So cost of a generation for generator 1 is 6559.3 rupees per hour. Similarly, you go through the cost equations for generator G2 and generator G3. Put the value of PG2 and PG3 that you got in an earlier step and try to find it out a value of FG2 and FG3, which will be 5282.4. And for third generator it is 1835.6. So how we can calculate total cost of generation by utility A? It is denoted as suppose FA. So we will add this 6559.3 plus 5282.4 plus 1835.6. If we add these, then we will get this is. So we can write, in order to produce a total demand of 700 megawatt, the area A1 will require to have cost of a generation 13677.245544 rupees per hour. Now similarly, we will find it out the values of PG3, PG4 and PG5 and also associated cost equations, that is C4, C5 and C6. We have to follow a same procedure whatever we have discussed in a earlier, that is in a utility B. So I will go in a quick manner here. So if you compare the cost equation with the data which is given to you, then you will get answer as A4 is 0.005282, B4 is 13.41 and D4 will be 950. Similarly, we have to do it for fifth generator and sixth generator in a utility B. So if you do this, you will get this answer. This will be your A4, this will be your B4, this will be your D4. Similarly, A5, then this is B5, this is D5, and A6, we can say B6 and D6. We have to use this value for finding out a value of a lambda. So we know what is the formula here of lambda. You just substitute. Now here in area 2, PD is nothing but 1100, which is earlier given in the data in a numerical. Now if you substitute B4 A4, B5 A5, B6 A6, you will get this answer as 6592. Similarly, if you substitute 1 upon A4 plus 1 upon A5 plus 1 upon A6, you will get the answer as 475.3634. So what is the value of lambda? Please try to calculate. You will get answer as 16.1813. Now just substitute again in the formula. PGI will be equal to lambda minus BI upon AI. Now please take here I equal to 4. So we will get lambda minus B4 upon A4. We know what is the value of lambda, B4, A4. So you will get this PG4, PG5 and PG6. Carefully observe whether that generator is going to produce the maximum power which will lie within the limit which is given. That is PGI, then PG maximum, whatever, and here will be a PG minimum. So if you observe carefully, whatever answers we will get, it will lie within this inequality constraint. So we can take it. If you add this, you will get the total power as 1100 megawatt. Now by putting the values of PG4, then PG5 and PG6 in the cost equations, F4 or you can say C4, then F5 or you can say C5, F6 or you can say C6. These are the equations that you have given in the given data. That is for generator 4, for example, it is 0.002641 PG4 square plus 13.41 PG4 plus 950. So you just substitute a value of PG4 that you got earlier in a previous slide, and you will get answer of cost of a generation by generator 4, 5 and 6. So if I want to produce the total load demand is 1100 megawatt, then the total cost of generation by utility B is 18564.857662, which we will obtain by adding FG4 plus FG5 plus FG6, which is equal to FB. So this is the total cost for utility A and B. So if we add FA and FB, this was already we have find it out in a utility A. This was the last step and we got this value. Then this is the value here we have we put here. So suppose total cost for utility A and B, if we want to find it out, this will be 32242.10321 rupees per hour. Now let's take two areas are interconnected. Let's say this is area A and area B, which is interconnected. Now what will be the total demand? Initially for area A it was 700 megawatt. For area B it is 1100. If it is interconnected, now it includes 3 generators. It includes 3 generators. So individual economic load dispatch already we have calculated. But if we consider this as a total area which is interconnected, then total demand will be 700 plus 1100, which is 1800 megawatt. And the total generators will be these 3 from area A and these 3 from area B. That is total generators will be what? Total generators will be 6 generators. Now solve this for finding the value of a lambda. Now what we will do, we will find it out the value of a lambda here. Again we will use the same expression what we have, and now instead of having B1 by A1 plus B2 by A2 plus B3 by A3 only, we will have here like this, lambda will be equal to PD plus B1 by A1 plus up to, it will be up to B6 upon A6 whole divided by 1 upon A1 up to 1 upon A6. So you know all the values, you try to substitute, you will get the answer for lambda as a 16.8807. Now what we will do, we will put the value here, we will put the value of lambda in the formula. We know PGI will be equal to lambda minus BI upon AI. So what we will get here, if we put it here, lambda equal to 16.8807, B1 A1, find it out PG1, B2 A2, find it out PG2, like that we will find it out first for PG1, PG2, PG3, and if I add these, then the total power which will be produced by utility A is 368.7311. Similarly, for generator 4, 5 and 6, we will find it out by using same formula, lambda minus BI upon AI. So PG4, PG5, PG6, we will get this much megawatt of a power. So total power generated is nothing but what? 590 plus 387.6927 plus 387.6927. So we will get answer as 1365.3854. Now by putting above values of Pg1 to Pg6 in given associated cost equations, then we will get the cost of a generation for G1, G2, G3, and what is the total cost of a generation with interchange. Now we are talking about interchange because it is interconnected with each other. So it will be addition of these three. So how you will get this will be Fg1 plus Fg2 plus Fg3, then you will get this cost, that is 7923. And the total cost for utility B with interchange, if you add Fg4 plus Fg5 plus Fg6, then you will get this answer 22940.4 rupees per hour. Now the total cost by utility A and B, how we will be able to find it out? Initially it was 7923, in the previous slide we have seen, and 22940.4, that also we have seen. So if we add these, then we will get the total generation of 1800 megawatt. It requires what? 306863.387936. Now what is the power to be interchanged? So how we have seen this interchange of the power? So this was the total power generated by utility B when it was connected. This is the total power which is which we got by the utility A when it was connected with B. So interchange of the power will takes from B to A. Okay, it will takes from B to A because it is a maximum minus minimum. So 265.3854 megawatt power, which is a surplus power in a area B. So it will be transferred from utility B to utility A. Note that the overall cost of operating both the system is now less than sum of the cost to operate the areas when each supplied by its own load. Now let me tell you the meaning of this. What is the overall cost when it is interconnected? 30863.387963. And when we find it out, economic load dispatch for area A, which was FA, and economic load dispatch for area B and its final cost FB. So if you remember, please go through that particular slide and please check what we did there. After calculating utility B calculations, we wrote there one statement: total cost for utility A and B. So it was what? F will be equal to FA plus FB, and we got their answer as 32242 point whatever something rupees per hour. So what we observe here, if we interconnect these two utilities, then the total cost of a generation is 30,000 something, which is less than that of individual cost of a generation, which is 32242. Now remember that the power generation by area A is more, which is 700 megawatt. So you will ask me, sir, how it is 700 megawatt? already earlier we have seen this, than that of a power generation by A when it is interconnected with area B. So this 700 megawatt we got in a case A. Case A means what? When only we consider utility A was acting alone. But when it is interconnected with a utility B, and now if you see the addition PG1 plus PG2 plus PG3, then you got this answer as 368.7311 megawatt. That is when both the areas are interconnected. Also, the power which is generated by area B when considered as an individual is less. Now if you see in the case B, we considered only a utility B. So what was the power generation? It was PG3, PG4 plus PG5 plus PG6, which was 1000 megawatt. It was the demand earlier. But when we interconnected it with A, then with interconnection, if we see the power which will be generated is 1365.3854 megawatt. You please see the slide where we have written PG4 plus PG5 plus PG6. So what we observe here? The power generation by area B when it was acting individually, it was less. But when it is interconnected with A, then it produces a more power, which is 1365.3854. So hence we can summarize this. If we have a area A, if we have this, okay, let me write it here. If we have area A without interchange, means what? When it was not interconnected. When it was not interconnected, in that case the value or the generation cost was 13677.24, and with interchange it was 7923. So instead of turning on remaining generators which are there, suppose if we have few more generators with area A, then instead of using its own spinning reserve, if we purchase the power from area A2, then the cost of a generation is minimum compared to that of its own. So therefore, how much saving will be there? Here the saving will be 5754.2455. If we subtract the 7923 from 13677, we will get this. But on the other hand, for area B, without interchange it was 18564 point something, but with interchange it was 22940. So what is increased in the cost? How we can find it out? If we subtract this 18564 from 22940.4, then we will get this answer as 4375. But remember, this is increased in the cost. This is increased in the cost. So how we will be able to find it out? Combine net saving. Just you subtract these two parameters. So 5754.2455 minus 437.54. So we will get 1378.703206. So individual area A1, the cost of a generation was different. For individual area A2 or utility B, it was different. But when it was interconnected, then we got some net saving, combined net saving. So this is the benefit of interconnection of a utility. So what conclusion here we have drawn? Utility A is generating at a lower incremental cost than utility B, because the cost of a generation before interconnection for area A, it was 13677.24, and for area B before interconnection it was 18564.85. So what you observe here, area A's cost of a generation is less, or we can say it has lower incremental cost than area B. Now if utility B were to buy a next megawatt of a power for its load from utility A with the condition that the price of a power purchased from A is less than that of a power generated from its own generation for next megawatt, then it would save money in supplying that increment of a load that we have seen in an earlier table, combined net saving. Utility A would be beneficial economically by selling power to utility B only if the utility B is willing to pay a price that is greater than utility A's cost of costing of a generation. In long-term interchange, the surplus power and the energy available energy should be available with one system, then it may wish to sell it to an interconnected system. In other time, the interchange of the power and energy is sold to an interconnected system based on when and if available. This is very important. Whenever it is required and if it is available, then only there will be a power transaction between the two utilities. So this is the proof. We can say whatever advantage that we have gone through earlier in the previous video, it is proven here. If excess power is there, then only it will be transferred from one utility to other utility, and the utility which is going to sell the power to other utility will get some kind of benefit. Individual utility, if it runs and if the interconnection is there, then there has to be some kind of difference between the cost of a generation. Thank you for watching this video. If you have any doubt, please feel free to ask the questions. Thank you once again.